In the beginning of 2024, I uploaded a video about developing a procedural mountain forest for my game. Since then, I've written various blog posts about the game's further development, but not made any new videos about it until now. The game has the working title The Big Forest, and one day I want to make a video about what kind of game it actually is. But right now I just want to show you how I've made the procedural terrain bigger, better and faster, so that it went from looking like this to this. I'm Rune Skorborg Johansen, and this is Rune Vision. Where to start? In my previous video, I had nice paths going through the environment, but they actually just went on infinitely along the diagonals of the terrain chunks without any destinations or branching points. To make things more representative of where I wanted to end up, I added placeholder towers to represent points of interest and made the paths go between those. There's occasional artifacts where the paths intersect each other, but that's a problem for later. Next, I worked on several improvements to the foundation of my generation tech. My procedural world generation runs on background threads using C# built in parallel for each functionality. In this video, the visualization on the right shows all the running tasks, with the small dots next to each line showing how many threads are currently working on that task. The dots piling up in the GPU get terrain data task means that the most time was spent getting past the formation data back from a compute shader. I wanted to try to do this work on the CPU instead, but using Unity's Burst compiler. Getting Burst working required rewriting parts of the code into Unity's high-performance C# style, which means static functions, no classes, and replacing arrays with native arrays. Native arrays are only 1D, so I had to write my own wrappers for 2D array functionality. But it was worth it. After Burst rewriting the getTerrainData function and a bunch of other ones, the overall generation became 3 times faster. This was really satisfying, and I had a bit of fun with this newfound generation speed, which could still keep up even when making the character go really fast. Next, I wanted to increase the view distance. Although I used highly accelerated aerial perspective, that means a blue tint in the distance, to create a sense of scale, you could actually only see less than a kilometer away. So far, all my terrain chunks had the same size. I knew I'd need to use larger, lower detail terrain chunks in the distance to manage a larger view distance without making the generation way too slow. I made 4 inherited LOD versions of my terrain generation layer, each generating 5x5 chunks around the player at a time, but each layer generating twice as big chunks as the last. Since larger chunks have the same resolution as smaller ones, they are not heavier to generate or render. I then ensured that larger terrain chunks are hidden if there are smaller terrain chunks that completely fill the same area. Now I had to simplify things in the larger, more distant chunks. The tree coverage is thinner to avoid the frame rate getting too low, and the paths are not generated to avoid the generation taking too long. But with these small compromises, the LOD system made it possible to triple the view distance to around 2.5 kilometers without any increase in the number of generated chunks or in the generation time. Using terrains of different sizes meant there was initially small occasional cracks visible between chunks of different sizes. Unity doesn't have any built-in solution for this, but I work around it by having the terrains overlap a little bit and implementing a form of terrain skirts. The Big Forest is built on my procedural generation framework LayerProcGen, which can be used to organize infinite generation into multiple dependent layers without prescribing any particular algorithms. I'd long been using it for my own projects, but in the spring of 2024 I started cleaning it up for a public open source release and improving its built-in debug visualizations. Here's a visualization of how the paths going through the landscape are built up in multiple layers, with higher ones depending on lower ones. This is how I generate highly contextual features, like paths based on pathfinding, that seamlessly cross chunk boundaries. In April 2024, I gave a talk about the framework and the philosophy behind it at the Everything Procedural conference. The talk is available online, link in the description. And shortly after, in May, I released the framework. Layer-based generation is a whole way to think about spatial dependencies for large-scale generation, so I also spent a lot of time documenting the high-level concepts, not just the implementation. LayerProcGen actually started over a decade ago for another game called The Cluster. I eventually shelved that project to make Eye of the Temple, but after releasing the LayerProcGen framework, I finally polished The Cluster enough to release it for free. It has some unique things going for it, so maybe give it a try. Okay, there are other aspects to the big forest than just its landscape, and I spent the next year working on those, like procedural creatures. But that's not what this video is about. I'd long needed a better solution for rendering distant trees. For performance reasons, games typically switch distant tree models with images. So far, I'd been using Unity's extremely outdated built-in solution, which is fast, but doesn't let distant trees cast or receive shadows. The result is a flat mass of color that destroys the landscape's sense of shape. I wanted to use a different technique called octahedral impostors, where trees are pre-rendered from many angles and reconstructed with a shader that behaves surprisingly like real geometry. But to make them fast enough performance-wise, I also needed a graphics technique called GPU instancing. I tried a third-party tool called GPU Instancer, but for my use case it suffered from rendering glitches and stuttering. Eventually, the author released GPU Instancer Pro and also fixed several issues I reported, making the approach viable in the summer of 2025. My old tree models weren't compatible, so I replaced them with a new set that I also preferred aesthetically anyway. At first, the new trees looked dull when placed in the game, but I got them looking much better with a number of shader changes. I removed the reflective sheen Unity adds by default and used a custom wraparound lighting function that's brighter in shadow. I also modified the shader wind animation so that branches sway without appearing to compress or stretch. And I got translucency working, allowing light to filter through the leaves. This is really important to how trees look, especially when viewed towards the sun. With the new trees working, the distant tree coverage looks much better. Gone is the flat mass of color, with the trees correctly casting and receiving shadows. Someone commented that the new trees look too rounded, as if shaped by a hedge trimmer. After experimenting with roughening up the mesh normals via an acid post-processor, I agreed it looked better. Finally, I added the sound of rustling leaves using the same point cloud sound system I developed for the water sounds in the previous video. By the way, I've since written up a blog post explaining how that works in details. After the tree overhaul, I worked on different aspects of the game, namely prototyping, game progression, dependency graphs. But again, it's not what this video is about. Then I spent a long time investigating and improving an erosion filter technique. I made a whole long video about that back in March and released the work as an open source shader. Since then, other people have made implementations of it for Unity, Unreal, Godot, Blender, Houdini, and more. For my own game's terrain, I had long mulled over how to combine the epicness of grand mountains with the what's around the corner intrigue of smaller cliffs and hills. And on top of that, how to meaningfully integrate my erosion technique into it. After a lot of fiddling over a few days, I felt I was onto something. This was in April 2026. The new mountains were a lot taller, so I added a new terrain LOD level, doubling the view distance again to around 5 kilometers. So far, I'd been calculating terrain heights on the CPU, but with the added erosion technique, this had gotten quite slow. But I found an undocumented way to write shared C# and shader code based on Unity's mathematics library. This way, early layers could spot sample heights for path generation on the CPU, while the final terrain is evaluated on the GPU. This made the generation much faster, so I was able to fly over the landscape at 300 km per hour. Now that the erosion was fast, I spent some time refining it further. I could add more erosion octave to amp up the strength and detail, and I also colorized the cliff color based on erosion more aggressively, which adds a lot to the overall impression. I actually don't use the mask-based erosion technique from my erosion video, since I don't want crisp peaks and valleys. Instead, I use a custom technique modified to my game's needs. The overall erosion filter technique is very flexible to modifications. If you want a large game world, you'll eventually run into floating point precision issues. Positions in games, for objects, cameras, and most other things, are normally stored as 32-bit floating point numbers with a limited amount of digits. The larger the numbers, the less precise they become, so if you move far from the world origin, things start to break down. To avoid this, my game uses fixed point numbers for its procedural generation. With 256 values per meter, they can represent distances down to a few millimeters, no matter how far from the origin. Their range is about plus/minus 8 million, the 32-bit integer range divided by 256. Well, that's the theory anyway. It's only here in May that I really put it to the test by placing the player 8,000 kilometers from the world origin. Predictably, there was a number of issues. The bugs tended to be subtle. For example, some code averaged 2 world space coordinates to find a point in the middle, but here the sum overflows the supported range long before either coordinate does. The division by 2 only happens after the sum has already wrapped around and become incorrect. The solution is to calculate the average in a different way, which avoids summing the coordinates. Rewriting all the noise functions to use fixed point numbers was more complicated, but that's too big a topic for this video. After a bunch of fixes, I could generate the world 8,000 kilometers from the origin without any generation errors. However, the numbers still had to be converted to floating point eventually, since that's what most game engines use, including Unity. Here's what the world looked like 8,000 kilometers from the origin. The terrain held up better than I expected, but the shadows were a mess and the UV mapping too. The way to overcome floating point precision issues, even though floating point numbers eventually have to be used for rendering, is to use a technique called floating origin. I used a variant of it called origin shifting. The idea is to separate the world coordinates used for generation from the scene coordinates used by the game engine. Whenever the player gets far enough from the scene origin, the player and the entire rest of the world is shifted back near it, effectively moving the scene origin to a new position in world space. With that in place, the game works just as well at plus/minus 8,000 kilometers from the origin as it does at the center. In 2 dimensions, that gives a square world of 16,000 kilometers across, or roughly half the surface area of the Earth. Now, this doesn't matter much in practice. A procedurally generated world is only as good as its variety, not its sheer size. But it does mean that I won't have to worry about the world size being a constraining factor anymore. The epic mountains and longer draw distance provided for some grand views, but the blue tint in the distance was a bit underwhelming. On a vacation in Japan the previous summer, I'd seen that while mountains in the distance get a blue tint, they approach a white color even further away, just like how the blue sky approaches white towards the horizon. In both cases, the color depends on how much atmosphere you're looking through. I even wrote a whole blog post about it. So I changed the fog implementation in my shaders to get paler at far distances too. This adds so much depth to the distant parts of the view, and I feel it makes the landscape breathe. I know there's techniques for more accurate atmospheric scattering, but this simple two-color gradient works great for now. I had sometimes posted videos of flying over the landscape, but it had always been on Rails. I got an itching for being able to set off and fly through the landscape manually, even if unlimited flight probably won't exist in the final game. While testing that, I was really missing sounds from the tree crown collisions, so I implemented that too with my point cloud sound technique. And I felt it oddly satisfying to fly straight through the trees and almost feel the impacts of the branches and leaves. And that leaves us at the present time. Of course, I have lots of ideas for future improvements, but for now this is it. If you liked the video, you can click the like button, and if you want to see more, consider subscribing. Till next time, bye!